All right. My name is Jungsang Kim. I'm a professor of electrical and computer engineering at Duke University, and also in physics. And also a co-founder of a quantum computing company called IonQ. So today we're going to talk about what you mean by practical quantum computing. This is a very interesting subject because there was a meeting I went to, and I talked about practical quantum computing several years ago. And one of the very renowned professor who's working on AI stood up and said, whenever you say practical and in quantum computing in one sentence, that's fraud. All right, so I take on these challenges. I'm sure there is some context by which that statement was made, and the question is understand that context and see if we can actually make practical quantum computers. Now, I'm not suggesting that we have practical quantum computers today, but we're getting so much closer to it every single day, and I think in a very close future, we may actually get to a practical quantum computer. So let's take that journey in it. So the question I think we discussed earlier today is about what is quantum computer? And quantum computer uses the principle of quantum physics. And here I take a couple of very famous quotes from Richard Feynman, who is a Nobel laureate for discovering a good chunk of quantum physics. I think he mentioned something like this: I think I can safely say that nobody understands quantum mechanics. And he's like one of the founders of quantum mechanics. And then he also, this is actually pretty important, so there are paradoxes. And we talk about quantum paradox, we talk about the many paradoxes here. And paradox looks like there are two things that actually don't make sense. They seem in conflict with each other. But his view is that paradox is a conflict between reality and your feeling of what the reality ought to be. So in one sense, there is a reality. And then in the other sense, there is our thought or our understanding of the reality. When they collide, the reality is always right. Meaning we actually have to then upgrade our model to make sure that we capture that behavior reality into our consciousness. And that is called science. Okay, so I think a scientist who feel like they understand everything is like the worst scientist. I think a real scientist should always be questioning, what am I missing? Because that's where all new interesting discoveries are made. So with that, let's jump into a brief history of quantum physics, of how it came about. And I mentioned that quantum physics is about 100 years old today, and this is the year of quantum science and technology celebrating the 100th year of the theory of quantum physics being rather complete. Now, let's actually roll our clock back to just before that, at the end of the 19th century. This is when the scientists and physicists had the most confidence. Okay, so in the 18th century, I think you guys all heard about Isaac Newton. So Newton came up with Newton's law, F equals ma. And then and this actually describes behavior of particles, like baseball we throw or the planets. And then at the end of the 19th century came Maxwell's equations. And this was actually a unifying theory that describes electricity and magnetism. And these all look like different properties of nature. But these four equations actually brought all of them together. And then it also reveals some new recognition that light is an electromagnetic field, for example. This is a very powerful period in science where the scientists, especially physicists, had a lot of confidence that we knew exactly what's going on in the universe. Now, I think mathematically speaking, these are what's called differential equations. Okay? These are equations that actually tells you how things change over time. And the flip side of it is if you knew the condition of something in the beginning, you can predict the rest of it exactly. Because a differential equation, if you solve it, if you know the initial condition, it will tell you exactly how the world is going to evolve. So this actually led to a deterministic and also reductionist view of the world, meaning you can break the entire universe into its components, and if you understood component, you understand the entire universe. Now that was the confidence that this science at the end of the 19th century gave us. But then comes the humbling moment, where in the turn of the century, when 20th century began, we start to see a lot of problems with this model. For example, this Maxwell's equations could explain a lot of behavior in light and others, but it also led to what's called the ultraviolet catastrophe. They call it catastrophe because based on this theory, the energy of a sun should explode into infinity. There's something wrong with this model that does not jive with the reality. And what people had to do is now kind of come up with different assumptions about the model or the theory to make an accurate description of the observations. Now it turns out that the assumptions we had to make was so counterintuitive based on these physics that we knew, and they call that quantum mechanics. Okay, but with those assumptions that are completely out of nowhere, but if we make that assumption that everything fits in place, means that that's a better model, a better understanding of the universe. Okay, so quantum mechanics was born. It actually, unlike some of these theories where Isaac Newton saw an apple drop and voila, in one moment this equation was formed, quantum mechanics wasn't like that. It took about the scientists and the communities about 2.5 decades of observation, crazy modeling, debate whether that makes sense, interpretation of what that means, which was so provocative to this world, deterministic and reductionist view of the universe, that actually really shaped a large scientific debate. But fortunately, about 100 years ago, that was all settled. Okay? And the settlement led to 2 superpowers of quantum physics that is so counterintuitive but has turned out to be true. And these 2 superpowers, and utilizing them, really is the second quantum mechanical revolution. Okay? And it's different from the other examples we've seen earlier today. It is exactly what quantum computing is all about. All right, so what does that look like? So the conclusion of all of these very sophisticated theory is there are 2 rules in quantum physics. Okay? The 2 rules is when you throw a baseball, we think about it as like an object that traverses in space, and we think of it as a particle. Like you can track its position and momentum exactly over time, and that's the Newton way of looking at it. But no, quantum mechanics says, oh, baseball thrown, or me talking to you here, it's all waves, like these murky waves in the ocean where it propagates and distributed all over the place. Now, if you have a wave, meaning if I drop a stone in a pond, a very quiet pond, and then I create these ripples of waves, if I drop 2 of them, these ripples of waves will propagate, and then they'll actually start to like run into each other, but they will actually pass on. Meaning this wave has nothing to do with that wave, and then they can coexist in this medium at the same time.
Right.
Okay? Now that is the principle of superposition. Superposition means I can have one wave and another wave that can coexist in time. Okay? So let's think about this atom, and in this atom is like a very small unit of matter, and it is formed with a nucleus and an electron going around it. And it turns out that by quantum theory, this electron can actually be in one of many, many states. So let's say we pick 2. The electron is in either state 0 or state 1. We're going to name the 2 states 0 and 1. What this means is this electron, if it's a particle, like a baseball, then it will have to be either in state 0 or in state 1. But if it's a wave, this particle can coexist in 0 and 1 at the same time. Okay? That's really strange, but it can coexist at the same time. And we write it down as a 0 and 1. It can actually coexist with 2 numbers, A and B. And those are numbers called complex numbers. It so turns out that's the way you have to be. And then, just like the classical laws of physics, we have a differential equation that tells you how this state will evolve over time. Okay? So in that sense, so I mean, this is a differential equation. I mean, it's a complicated equation, but it actually tells you exactly. If you knew A and B at time 0, you know exactly how it's going to evolve over time. All right, so in that sense, it's not that different. But then comes this weird thing called rule number 2. Rule number 2 is if this atom is isolated by itself, that nobody's looking at it and we have no idea what's going on, then this is true. But the minute we try to understand what it is and probe it, then the superposition collapses. Meaning, while this atom, this electron in this atomic state can be in 0 and 1 at the same time and evolve accordingly, when you try to make a measurement, observation, you ask the question, are you in 0 or are you in 1? You will actually have to decide. And that decision is really a collapse. All of a sudden, it picks one or the other, and that process is not described by differential equations, and it's like throwing a dice.
So the two rules are completely different.
The two rules are completely different, completely uncorrelated, and there's no reason why. That's just the way it is. Okay? Now, it so turns out that this randomness is not completely mysterious. It actually does tell you the probability by which you can find a 0 or 1. Okay, there is a probability, and that probability is actually given by these numbers. Okay, so if this is 1 and that's 0, if A is 1 and B is 0, then you're always going to find this in 0, meaning you're going to find this in 0 with a probability of 100%, and the other one is not. But if A and B are exactly the same, then it's really 50-50. Okay, so this time evolution will tell you how it evolves, but when you observe it, it's going to pick one. And the probability of which one it picks is given by this equation. That's the rule of quantum mechanics. Okay, so these are the two rules. Okay, so that's very different, right? We know, in Newton's law, F equals ma. If you apply some force, then particle accelerates proportional to that. That's the law. Here it's very different. It tells you how it evolves, but when you observe, it collapses. All right? All right, so what does that lead to in terms of its superpower? The first superpower is quantum superposition. As I said, the electron in this atom can be in state 0 and in state 1 at the same time. Okay, so this means that I can be here and I can be here at the same time if you don't look. It's like magic. Does that make sense?
Professor,
Yeah.
I'm sorry, but I just don't understand how number 0 and 1 exist at the same time.
Yeah.
Could you perhaps explain more simply, please?
Yeah. So, unfortunately, I can't explain more simply because that's the most simple and fundamental laws of physics. But I can give you some examples, maybe an analogy to help you think about it. Okay, so let me give you an example of this. Let's say I pick a coin, I flip a coin, and the coin is spinning in space. Okay, so while it's spinning, I don't know whether it's going to land in heads or in tails. So while it's spinning up there, while you have this like uncertainty going on, until I pin it down, I can say the possibility of this guy landing in heads and tails coexist.
Uh-huh.
Yes.
It's like Schrodinger's cat.
Exactly.
Yes.
Right? It's like Schrodinger's cat, where a cat can be live and dead at the same time. If we don't look. Now, there's some caveat to that because that Schrodinger's cat is really like it doesn't make a lot of sense. But people have a much better understanding of how quantum systems in the subatomic world actually kind of translates to classical world that we actually live in. If it's a more general theory, it should also explain that what we're seeing every day. And indeed, quantum mechanics actually includes all of the classical physics that we know. So it actually, at some point, the quantum laws of quantum physics do reduce to classical physics that we know. So there's no inconsistency. It is just a bigger theory. Okay? But this, we started talking about the coin. When the coin is flipping up in the air, it can be in 0 and 1 at the same time, and I want to pin it down. I don't want to pin it down. Now, but when it lands, when you observe, then it flips, it has to pick one. It cannot be in some ambiguous state by the time it falls onto the ground. It will have to be heads, it has to be tail. That's kind of what it is. So that's the analogy, right? So quantum state is we have a coin flipping into space, in the air, and only when it lands, when we want to understand what's going on, then it will actually have to pick one. So we're going to allow that ambiguous state or that multiple state being at the same time to be a reality of the universe. Okay? Now, this is strange, right? Especially to the deterministic view that even the most famous scientists had. So our favorite physicist of the 20th century, Albert Einstein, didn't like this idea. He says God does not play dice. Now, is that a fact or is that his conviction?
His conviction.
It turned out that was his conviction. He just did not believe that nature should be probabilistic. That's the conflict and paradox. But the reality is that the nature is probabilistic. It does have the randomness built into the universe. And therefore, universe is not deterministic. And that's good for us. I don't want to live in a world where all of my future is dictated for us.
True.
Right? So it has some philosophical meaning too, but it so turns out that nature is that way. Okay? Now let's move to the second superpower called quantum entanglement. Okay? Now quantum entanglement is now we're thinking about two atoms, meaning the electron in this guy can be in 0 and 1 at the same time, and the electron in this one can be also in 0 and 1 at the same time. Now I can actually think about a superposition state that looks like this. Okay? This is a superposition of both electrons being in 0 and both electrons being in 1. And it's a superposition of that. Mathematically, I can write it down. And because these two states where both electrons are in 0 and both electrons are in 1 are allowed quantum states, I can write down a superposition like this. Okay? Now, this has a weird property that makes no sense. Meaning, if I observe, let's say I have this state that's given to me, and then I can actually push this particle pretty far out, and I only look at this guy. I'm not going to even look at that one. And when I make a measurement, this is going to either collapse to head or tail. So again, let me make sure that this is a state where the two coins are all flipping at the same time. Okay? But this only has the possibilities of both being in heads and both being in tails. So when I go and look at my first coin and let it drop, and if the first coin landed in heads, the second coin absolutely also lands in heads. But if it lands in tails, the second one also lands in tail. Okay? So this means, this is really weird. The observation is, if I prepare this entangled state, I flip the coin, they're all flipping. I don't know which way it's going to land. But what I do know is when one of them lands in heads, the second one lands exactly in the same state. Somehow there's this magic link between these two atoms that when one collapses into 0, then the other one also collapses into 0. Okay, now that's really strange too. Okay? That's really strange. And sure enough, our favorite Albert Einstein called this spooky action at a distance. So Albert Einstein came up, as we know, with this theory of relativity, and his claim was that information, or you cannot communicate faster than the speed of light, and this seemed to violate it. Meaning I prepare this entangled state, I send one to the moon, second one I have it here. Once I measure it, and if it comes in heads, I know immediately that this thing that is like way, way far out in outer space also collapsed in heads in time scale that's much shorter than the speed of light that can propagate. So that doesn't make any sense, right? Now, and so he called it a paradox. It's called that Einstein, Podolsky, and Rosen, these three people came together and wrote a paper in 1936. It's called the EPR paradox, Einstein, Podolsky, Rosen. Okay? Now, it so turns out that when you dive into the details, this actually does not violate causality, meaning it does not mean that information can actually travel faster than speed of light, but this kind of what's called a non-local correlation, meaning these two things that are connected, and they're not local, because one can be in Earth and the other can be in Mars, and this correlation still exists. That is allowed by the laws of quantum physics. Okay? Now, so this EPR paradox became a big question. And then, people in the middle of last century, especially this person named John Stuart Bell, came up with a mathematical model and an experiment that we can in principle perform to tell if Einstein was right or wrong, meaning this non-local reality exists or not. It's fascinating because you can design an experiment to prove it. Okay? So there has been, and this was in 1961, and people actually try very hard to figure out, can I actually do this experiment? And then these three gentlemen and their teams, of course, John Clauser in 1970s and Alan Fay in 1980, and then Anton Zeilinger in the 90s, they actually successfully carried out this experiment. They designed a system where you can manipulate quantum systems down to the atomic, in this case atoms of photon level, and perform this experiment to prove that Einstein was wrong. Okay, and in 2022, they were awarded Nobel Prize in physics for actually proving that. And this actually proved that this superpower does exist, right? And that became the foundation for this quantum information science, which also led to quantum physics. So these were, as I said, these experiments were done in the late 20th century. So I would categorize 20th century as first quarter of a year, lots of confusion. We just realized that the physics that we knew at the end of the previous century was not sufficient. And then we spent the first quarter of the century trying to figure out what the right model is. And then lots of debates. People said, this makes no sense. A lot of people questioning whether that reality was accurate. It turns out that in the latter third of the century, we actually started to create technologies where we can actually manipulate these atoms and photons and quantum states much more accurately to be able to design and prove that these things are actually reality of the universe. So it came from like discovery, lots of debate, and then proof. Now, at the end of the 20th century, in order to prove this, we actually had to develop technologies to manipulate single quantum states and things like that. And that became a new tool. And by the time we start to recognize this quantum computing with the superpowers, we can do unusual things, that really opened up the 21st century. And I can't believe that a quarter of the 21st century is already gone. But in the first quarter of 21st century, scientists and engineers like myself, we decided to figure out how to utilize this as a tool to build new computers. So we're actually going from the 20th century, where we were spending a lot of time understanding quantum physics, to now actually using quantum physics, the second generation quantum revolution, to build new tools and computing machines. Okay, so that's kind of where we are. This I give you a little bit of a background of why this is so timely. And then, this actually rolls the clock back to maybe in the 1970s, early 1970s, and then this is the turn of the century. Okay, so this is the last third of the century and the first quarter that we've been living through. You all heard about Moore's law. Have you heard about Moore's law?
No, I haven't, to be honest.
Oh, you haven't heard about Moore's law. Okay, but you also know that within your lifetime, every couple of years, your cell phone or your computers get so much better and faster. Almost like doubling every year.
For sure, yeah.
Yeah, that's called Moore's law. Okay, so Moore's law was invented. It was actually declared by Gordon Moore, who was the founder of Intel in the 1970s. And he actually observed over the years, and it's not like a law in the sense that this is how the world works. It's actually an observation that every 18 months, your computer gets twice as strong. That's called the Moore's law. And it sustained itself over the course of the good part of the last 3 decades of the 20th century, well into the century. Now, what does that mean? What does it mean by doubling every 18 months? It means that every 30 years, your computer gets 1 million times better, 1 million times more powerful. And it is an exponential curve. Okay, it's actually doubling every 18 months. Now, there's not too many examples like this. For example, if you drive a car, people say, if your car speed can double every 18 months, we'll be driving at the speed of light today. Okay, so this is actually not very common. Something growing exponentially over time is actually extremely uncommon. But in Moore's law, we're able to do this. What this means that your computers got more powerful and cheaper, more accessible every single year. And that's why in the 80s, I bought my first computer in the 80s. It was a very crappy thing that you can do very little things with it. And it was big, right? It couldn't fit in your pocket. The computers that we have today, like even a single cell phone, is so much more powerful than the computer that powered humanity's first trip to the moon by a factor of 1 million. what you carry in your pockets today. And that's only possible because of this Moore's law and the technology trajectory. And you can also, it's also one of the other dimensions is if we can actually jam in more and more of these transistors, which are the component devices that make up your computer chip, so that in a small chip that you carry in your pockets, in one chip, today we have like 10 billion transistors in it. And people never thought we could build that complex of an object in the past, but nevertheless we managed to do it. Now, the interesting thing is this exponential curve, which looks like a straight line here, is really slowing down. Right, you can see that we're starting to hit some limit, because at some point the size of a transistor will become the size of a single atom. And I don't think we know how to make computers with a smaller part of an atom. Not only that, this is again Richard Feynman, when you go down to these very, very small devices, your classical world doesn't work anymore. The laws of physics that we used to create these devices don't work anymore. Now we're in the realm of quantum mechanics, not like in the Ant-Man quantum mechanics, or maybe. I think conceptually, scientifically very different, but conceptually we're going to a very, very different regime where the laws of universe looks very different, where these two superpowers exist. And that means that actually spells the end of Moore's law. And that's in one sense very scary, but he had the foresight to see that this is not a risk, but this could be an entirely new opportunity for building new computers that work on different principles. And he speculated that would be much more powerful, although it would be extremely difficult to do that. 60 years down to his first prediction, we're actually building quantum computers today. Okay? All right, so we talked about these superpowers, and let's say you have a vague understanding of what it is. This is like, now we understand Superman can fly. Now the next question is, what does that mean? I'm not asking the question how and why, but what does that actually mean? What can Superman potentially do? And that actually starts to become a region of logic. Okay. All right, so I'll tell you the good news. Let's say we actually have quantum bits. Quantum bits are these quantum version of bits that can be in 0 and 1 at the same time. Let's say we have 3 of them. Okay? It turns out that these 3 can all be in 0, or it can be 0, 0, 1, 1, 0, 1, 0, and actually this is 1, 0, 0. Or it could be, so it could be in one of these 8 states. There are 8 numbers it can represent, going all from 0, 0, 0 to 1, 1, 1. Now, classically, if you have a register, it will take only one of these 8 possible states at any given time. But quantum mechanically, because now we have these 3 coins flipping up in the air, it can actually take all of these 8 possibilities at the same time until it falls down onto the ground. Okay? And that's actually, in 8, it doesn't look very fascinating or impressive. But let's say we go to 300 bits. Okay? The 300 qubits it actually, by the time you get to 300. Now, keep in mind that if you look at your cell phone, we actually have typically 250 gigabytes of memory. Yeah. And that's 200 billion times 8 states, which is actually a couple trillion states. So like a couple of trillion bits classically is no problem. It's not too many. And it's a lot. It's not too many. We know how to build them. Here we're only thinking about 300 qubits. 300. Very, very small number of qubits. Now this can actually now be in one of 2 to the 300th power of states at the same time. Now how many is that? Number of states possible with 300 qubits is more than the number of atoms in the universe. Which means that if you were to build a classical computer that can represent all of these possibilities at the same time, you can never build it. Meaning even if you utilize all of the atoms in the universe to represent one of these states, you can never run through them in any reasonable time. Yet, quantum mechanically, if you flip these 300 coins in the air, and if you can actually control that state while it's up in the air, you can manipulate this many states at the same time, which is a fantastic opportunity.
Wow.
Which means that if you can successfully use this, you'll be able to do things you will never be able to do using a classical computer, ever. Okay? So it's not just a better computer. We'll be able to do a different class of things you're never able to do. Right? Now, that's fascinating. But at the end of the day, this universal, the number of possibilities is more than the number of atoms in the universe. All of those possibilities we can't deal with them. Because at the end of the day, we actually have to make a measurement and read the answer. When these 300 coins fell on the floor, it's all going to create one possible state. Some coins will be heads, some coins will be tails, and it will actually have one of these possibilities that will show up. Which means that although there's all these possibilities going on in the computation, at the end of the day, we're only going to get one result out. Okay? So what this means, this is somewhat depressing if you think about it, because I can do all these computations in all these states, but if the answer is distributed in all possible states, then I actually have to do this infinite number of times to actually get a sense of what the answer is. And that is where this naive model of massively parallel computing actually fails. But there's always smart people who come up with very exciting innovation, and that actually happened in the early 90s with people like David Deutsch and others, who actually recognized that this superposition of states, which are like waves, can actually interfere. What this means is if you have two waves coming like this, and if they come to a rising time at the same time, then they can actually rise very fast. But if they come out of phase like this, then they cancel each other to be exactly zero. That's what waves do. So what this means is, remember these coefficients, the numbers like these numbers, right? They can actually now start to interfere. And if you design a very smart quantum algorithm, then you can actually, at the end of, during the algorithm, it actually explores all of these possibilities that are exponentially many. But the algorithm brings it to the fact that only the right answer, the probability adds, and all the wrong answers, the probability gets completely depressed. What that means is when you make a measurement, you're guaranteed to get the answer. And that's the genius of quantum algorithm that we actually have to invent and continue to explore to actually really take advantage of this. All right, so that's the abstract, right? That's kind of how it works. And then now let's actually show an example, okay? Okay, now Superman can fly. What can it do? Can the Superman fly fast enough to reverse time? Is that kind of an example of what we can do? Okay, before we go there, as I mentioned, these quantum computers a fundamentally different way of doing computation. It's not a better way to do it. It's a fundamentally different way. Okay? So one of my colleagues, Bill Phillips, who won the Nobel Prize in 1997, once mentioned that if you think about a quantum computer and a classical computer, there's some difference between them. He said that the difference between a quantum computer and a classical computer is much more different than a classical computer is from an abacus. Okay, so you know what an abacus is. It's an old tool people use to add and multiply numbers. And of course, classical computers, in our minds, are infinitely more powerful than that. But his point is both of these use classical representation of information, meaning whether it's an abacus or computer chip, it can only represent one state at a time. Okay? It's just much more powerful version of an abacus, but it uses the same principle. Whereas quantum physics, we're using fundamentally different mechanism to actually do computation. So it can never be replaced by a classical computer if it actually works. All right. So then the next question is, why is it interesting? An MIT professor, Daniel Kleppner, once said, anything you can do in classical physics, you can do better in quantum physics. And another colleague from IBM, who invented some of these protocols, said a classical computer is a crippled version of a quantum computer, meaning a quantum computer actually encompasses all classical computers, except it's a bigger set. It does not mean that quantum computing technology is more advanced, but in principle, it actually includes everything classical. So let me give you an example of why this is interesting. Okay? Let's think about a mathematical problem of multiplying two numbers. If I give you 3 and 13, we know exactly how to multiply them. And that multiplication mechanism is actually relatively straightforward. Even if I gave you two very large numbers, a second grader can actually multiply them based on the algorithm we run. It's a very efficient algorithm. Okay? But if I gave you a product of two numbers and ask you for what are the two prime numbers that you have to multiply to get to this, it turns out that this algorithm is not easy. Okay? When it's small like 39, yeah, you can guess. But when it's a big number like this, it actually takes a long time because we don't have an efficient classical algorithm that's known today to crack this. So we basically have to try each and every number. Okay? And every time you add a digit, it becomes 10 times more difficult. And by the time you add enough digits, it becomes very, very difficult very quickly. So difficult that in order to factor a number that is maybe 20, 30, 40 digits long, maybe 100 digits long, it will take computers the age of the universe to actually find the factors. Okay? Now, people recognized this algorithm in the 70s and decided this is a trapdoor problem. Trapdoor problem means it's very easy to go one way, but it's very hard to come back unless you know exactly what the answer is. It's like, if you watch Harry Potter movies, they walk into Diagon Alley and there's like all kinds of bricks. If you know exactly what brick to press, the door will open. But if you don't know, you got to try everything, right?
Yeah.
So it's very similar to that. So this trapdoor problem is actually used for encryption. The encryption we talked about in the context of the cryptocurrency of Bitcoin. Okay, so when you try to send your credit card information to your favorite store to buy something, let's say you want to go to Amazon or Coupang, whatever your favorite store is. Their server will actually pick two prime numbers and multiply them, which they can do very easily. Okay, and then they create this big number, just like this one, and then they put it on the website, so everybody can see it. What your phone, when you're buying, does is it downloads that number, and then takes your credit card information and scrambles it using that number, and then now you send it back, or you can might as well publish it on a website. Everybody can see. Okay, so a hacker can have your key, and can also have your encrypted information. Okay, but unless the hacker knows how to factor this number, it cannot unscramble and extract your credit card information. Whereas the server on the other side started off with the number they know, so because they know that number, they can actually unscramble the information and extract your credit card information. That's how we transfer information safely, okay, using this trapdoor problem. So this is used all over the place, not for like national security, but also on day-to-day transactions. Okay, like our entire financial system today has evolved to depend on this. So the way that quantum computing actually solves this problem is, remember, there's all these infinitely large number of possibilities. In this case, we start with 39. There are 39 possibilities. We can prepare a quantum wave function. Wave function is this quantum state to have equal weight on all of these things. And that's very easy to prepare, it turns out. Okay? And then we run this algorithm called Shor algorithm. And the Shor algorithm will actually evolve this state while it's up in, while all the coins are spinning in the space. And then it will actually evolve into a state where at the end of the process, all of the probabilities actually collapse into 3 and 13. And then you let the coin drop. And it will either collapse into this or that with 50-50 probability. And everything else will be 0. And then all you have to do is read what the coin says on the ground, and then voila, you got the factor, roughly speaking. Right? So that's the power of quantum algorithms. And although we have found this very specific example in crypto systems, people believe that when it comes to understanding materials, chemistry, optimization, machine learning, in applications like finance, logistics, and all of these problems that we actually have a computational challenge, we do believe there is contribution and impact quantum computers can make in this very large set of applications. Okay, so that's why quantum computing is important.
So, Professor, I'm sorry to interrupt, but you just mentioned that these quantum computers can even break through encryption systems. So, if that kind of destructive computing power becomes a reality, what does that mean for the security of our everyday lives?
Yeah, that's a really fascinating question, and you're not the first one to ask it. Right? So when Shor algorithm was discovered, it actually first shocked the intelligence community, because well before we go into the encryption, because back in 1994, we did not have a lot of e-commerce, meaning internet wasn't very widely spread, and therefore we were not doing a lot of online transaction with that yet. But a lot of the national security information was encoded using this mechanism. Okay? And some of these security informations, they want to keep it secret for like 30 or 40 years, right? Before it was okay to reveal them. So people got really concerned, and people started to say, okay, what does it mean? Can we actually build this kind of a machine? Well, in principle, we can, but in practice, how long it's going to take, what it's going to cost. But also at the same time, people are starting to think about, okay, are there encryption techniques that are not based on necessarily this factoring problem, that are going to be robust against these quantum mechanical computers? And that question is still open, but I think people are making a lot of progress. It turns out that about 6 or 7 years ago, internationally, there was a very coordinated effort to design and implement and eventually deploy new encryption techniques that will be robust against future quantum computers. Again, these are not provably secure, but practically it will take even much more advanced technology to attack that. People believe that developing such an algorithm and implementing it and changing everybody's devices to that secure encryption platform is going to take a lot of time. We probably know about some grandparents who are still carrying their 2G phones, right? It's very hard to replace everything out. Yeah. But any vulnerability in the network can actually compromise the security of the whole thing. So we actually have to make a complete migration before quantum computers capable of attacking these things come about. So people believe this is going to take decades to do it. But people also believe that quantum computers capable of cracking these codes are probably a few decades away, but it's a race. On one side, we try to come up with the next generation encryption system and deploy quickly enough before this attack becomes real. And on the other side, people are starting to develop new quantum computing technologies that may be able to threaten that. So that's kind of what's going on. And I think it's a very healthy and interesting evolution of technology. So let's then move on and think about the reality, okay? So we discussed that at the end of the last century, people started to build up techniques to control these quantum systems, and now they're putting that technology to use to build this fascinating and like a phantom machine, what people once thought about as a phantom machine called quantum computers. And here I'd like to quote Arthur Clarke, who's a very famous sci-fi writer. The only way of discovering the limits of the possible is to venture a little way past them into the impossible. So when we started out, these ability to manipulate quantum systems was so premature. We were able to do it, but very premature. And the ability to do it well enough to build large-scale quantum computers seems like a huge gap. And that gap is still quite large, but we made a lot of progress by asking, and developing new technologies to do that. So we're kind of, as some of you said, it's like a unicorn. Does it actually exist?
Yep.
And we're actually inventing and actually building that unicorn. So in order to represent quantum information, we actually have to come up with a physical system that can represent that qubit, and that's called qubit. And we can use two approaches to building quantum computers. One is, and these qubits are basically the building blocks of quantum computers. And one approach is to use what's called the natural qubits. And these are individual atoms. And here I'm thinking about an atom. And I can actually strip an electron out of an atom, and that becomes an atomic ion. Okay, it's an ion because it's holding charge, but it still is a single atom. There are atoms where you don't pull those out, and therefore the atom remains neutral. And so these are atoms. And photons are particles of light. We can actually create and detect particles of light quite well. Actually, I did my PhD thesis on generation and detection of these particles of light in the late 90s. But these are starting to become accessible. A lot of the like the Bell inequality test was done by the single photon states and things like that. So these are qubits given by nature, and therefore they're identical. If you pick an atom, the same species, same isotope, you can pick that atom anywhere, and they're exactly the same. We can make 100 atoms, and they're exactly the same. There's no manufacturing variation, which is the advantage. But we've actually never built very complicated systems out of these qubits before. For example, with semiconductors, based on Moore's law, we started from a very crude device, but we know how to make tens of billions of these things in very small format factor today because the manufacturing technology has matured over time. For these new types of qubits, we don't have that technology. And therefore, there's a lot of technology invention we have to do. And then the actual manipulation of qubits actually is subject to some errors, so we have to worry about that. On the flip side, there's another camp of scientists and engineers who think that we can actually build these things. Just like we build transistors to represent our classical computers, they feel like we can actually manufacture quantum bits using technology that we have. And these are examples include these little circuits built out of superconducting material where the resistance of a metal goes to zero, like completely disappears when you cool it down to low enough temperatures. Quantum dots are where you confine some of these electrons in a very, very small space inside a material, and many other examples. So these are fabricated qubits, meaning they don't naturally exist in the real world, but you actually intentionally make them using very mature manufacturing technology that we have developed in other areas, like semiconductors. But of course, the downside of it is if you make two of them, they're never the same. Okay, there's some manufacturing variation, so you have to be able to cope with that. And then because these atoms, these qubits are embedded in solid. Now we talked about observation and we talked about us, but in principle, what the observation means, if there is somebody else, not us, but somebody else looking at it too, then it will actually collapse the quantum state. And that somebody else doesn't have to be a person. It could be a probe that somebody else uses, or it could be the environment. If there are other degrees of freedom surrounding the qubits, and if it interacts with it, in principle, I can look at that to learn about the qubit. So when that happens, the quantum state actually collapses. Because these qubits tend to be embedded in solid, there's lots of vibrations and other electrons and things like that that are potentially interacting with it. And therefore, the qubit actually goes through constant interaction with others, which tends to kill the qubit very quickly. So these are some of the challenges that we actually have to overcome. In today's lecture, I'm going to focus on the technology that I worked on, which is based on these trapped atomic ions, right? It's a very confusing state today just because there are so many different scientists and so many different engineers and so many different companies who are trying to build quantum computers out of all of these possible technologies today. Yes?
Professor, so among all of those technologies you mentioned, so the one that is the most advanced in terms of commercialization is then the trapped atomic.
It is one of them. I think one of my colleagues once said, getting to a useful quantum computer is like a marathon. And the technology today, we are just at the 1 mile mark. So it's hard to tell who's going to win. But today, there are clear leaders at the 1 mile mark. Okay, and atomic ions is one of them, and superconducting circuits is another. These two are probably the most mature technologies, although some of these other technologies are really speeding up. We're trying to catch up. Okay, so again, I have to say probably these two guys are next in line, right? They're somewhat behind, but they're catching up. So exactly who wins the race, we'll have to see. But that acceleration is completely dictated by innovation that we have to actually overcome the challenges that we have. Okay? All right. So let me tell you a little bit about our technology. So this is an ion trap. Okay? Ion trap means that we can actually trap these charged particles in space. And this is actually a semiconductor chip that we work with one of our partners at Sandia National Lab to make. And that thing that looks like a bow tie is about 1 centimeter in size. And that little isthmus in the middle is basically a few millimeters in length. And that in the middle here, there are lots and lots of little electrodes that actually create the electrostatic potential to trap these atoms. Okay? So the picture you see here, a bunch of dots, these are 80 individual atomic ions, individual atoms of species called ytterbium. Okay? So each of these dots is one atom. And it's actually floating in vacuum.
In vacuum?
It's floating in vacuum. This whole thing is in vacuum. And vacuum makes it very well isolated from the environment. Okay, it's not interacting with it. It's really sitting in vacuum. And it's like we create a bowl to hold these atoms, and then we throw these atoms in. And because they're charged, they repel each other. And then between the confinement and the repelling, they actually form this very, very nice one-dimensional crystal. Okay, so that's our qubit. Now the separation of these atoms is just a few microns. A micron is 1/millionth of a meter. And by comparison, the thickness of a human hair is about 100 microns. Okay? So the length of these ions, 80 ions, is just a few hair width wide. So they're really, really small, individual atoms trapped in very little tight space. The real advantage is for all of these atoms exactly the same. And then we can actually use external control fields like lasers and things like that to do a fully flexible control of this. So this is our quantum system that we work with. Okay, like science fiction, but it's actually very real because people have been using this kind of a system to build atomic clocks. We talked about GPS. The GPS runs based on atomic clocks. So this technology has been pretty mature for a while. So here I show you a blow up of that isthmus. Okay, and you can see that this little segments, those are electrodes, and we can actually control voltages on that electrodes to move these charged particles around. And here I show you a video clip of building up like a 23 atom chain, a crystal of 23 atoms. What we do is we load atoms one by one here, and when we have the atom that we want, we're going to move it by changing the voltages, and then we accumulate them in this middle region, what's called the quantum computing zone. And here now we have done this 23 times and created 23 ions, and then we can actually move the potential, stretch them out, make them equal spacing, we zoom in, and that's good to go. That's how we build it. Okay? Although it looks like magic, it's actually not all that hard to do because everything we have done today is completely classical. We take individual atoms, we trap them, and then we accumulate them. All right. So once you have it, then we have to control it. And controlling this quantum computer, we actually do it with laser beams. And what we do is we start with a single laser beam, and we split it, either passively or by actively tuning them. And we make sure that we align each of these laser beams to individual atoms so we can actually turn them on. And then that's a circuit. What we do is initially we shine some laser beams to prepare all of these atoms in one state so that we know exactly where we start. And then that is the quantum circuit, which is made up of these interactions and switching of the states. And we completely program and control that by shining laser beams on them. Okay, and this is all done by computer programming. And then all of these circuits actually do the interference of the quantum logic so that at the end of the day, you create the final state. What you do is you shine another laser beam, and then the coin flips, either into heads or tails. Okay, so some atoms will glow, others will not. The ones that glow is 1, the ones that don't glow is 0. And then you read it out at the end of the day. Okay, that's how a quantum computer works. Okay, so this doesn't look like a computer, very much like a computer at all. Very exotic stuff. But remember, a quantum computer does not have to look like a classical computer because it is so different from classical computers. Okay, we don't have to use classical computer technology to build quantum computers. Actually, that's very hard to do. All right, so what is the advantage of using these trapped ions? First, you start with atoms, so every qubit is exactly identical. So you don't have to worry about manufacturing variances. The second is because they're so well isolated, because these are atoms floating in vacuum, so it really does not interact with anything else. And therefore, the atoms are very well isolated. Unless we actively probe it, it is actually in the dark. In the dark means nobody's observing it, not even the environment. Okay? So you can get the very, very high quality of gates. But actually, there's a lot of really interesting architectural advantage too. Architectural advantage means, when we think about these computer chips, we use these transistors to build the circuits. But if you look at a CPU made by Intel and a GPU made by NVIDIA, they use the same devices. But when it comes to AI training, GPUs are like 1,000 times faster than CPUs. And it's not because of the device. It is actually the way that the devices are connected to do function. Okay? And because GPUs are designed to do massively parallel computations, and that's how we architect them, they can actually do machine learning tasks really fast. So what that tells you is even if you use the same devices, depending on how you structure the control in the system, based on a given task, your computer can perform massively different performances. So here I give you an example. In this example, if I have 23 atoms like we have seen before, it so turns out that I can, just by controlling the laser beams, I can actually make any two ions, any pair of ions in that chain interact just by programming. Okay? And so these are actually connected virtually by this charge interaction, Coulomb interaction, which is repulsion of the same charge. And I can use that to make arbitrary connection between any atoms in the chain. And that is somewhat different from traditional way we think about building circuits. In the traditional way, we have transistors, and we actually have to connect them with wires. So if they're connected by wires, we can actually make them interact. But if they're not connected by wires, say I have a transistor here, another transistor far away, and they're not directly connected by a wire, then we actually have to do a lot of interactions to exchange them. So the connectivity of how the qubits are connected to each other is much more universal in our architecture than others. And this can sometimes give you a huge advantage when it comes to a real quantum algorithm you want to execute. Now, if you know what the algorithm looks like, then we can build a system that does it really well. But if you don't know what the algorithm looks like, then we don't know how to optimize it. And today, we have very little idea of what the killer application in quantum computer will look like. We're still in the process of searching for many different possibilities, and therefore having a processor architecture that is very well connected, that can run algorithms of any structure, gives you a huge advantage. All right, so with that, let's think about what quantum computers can do. And this is just one glimpse of all the things people are exploring. But here, I want to project that quantum computers can actually be practical. Okay, now, the example I'm going to show you is such a simple one. So we are not actually beating classical computers. But this actually shows you that quantum computers can actually start to do really interesting problems. Okay, let me start out with a machine learning example. Okay, now if you look at these pictures, what do you see the difference between the top rows and the bottom rows?
One's all cats, one's all dogs.
Yeah.
Great, right? The top is all cats, and the bottom is all dogs. So this is a very typical AI or machine learning problem. Can we actually build a mathematical model in a computer that can differentiate dog pictures from cat pictures? And this is called classification problem. Okay, two classes. One class is a picture of dogs. The other class is a picture of cats. And can you build a machine that actually differentiates the two? And this is exactly how we learn as a baby. When a baby is born, I'm pretty sure they've never seen a cat, they've never seen a dog before. But then over time, the mom and dad tells you, like, okay, that's a cat, that's a dog. And what the babies do is they start to actually identify some features on these images that are characteristics of a cat and characteristics of a dog. And based on that features, when they're given a new picture they've never seen before, they can actually make an association. So in the brain, somehow we're connecting our neurons to build this model that recognizes the dogs on one side, the cats on the other side, based on some of the features. Now, sometimes you can come up with a picture of a weird animal that kind of looks like a dog and it kind of looks like a cat, right? Sometimes those cats that look very much like dogs and vice versa exists. What that means is some of these key features that we have used to utilize to differentiate these two images, this animal has both. And then you get into this region where you can get confused. And how well we can do that, the more experts and more training you do, you can actually tell that better. But that's how this machine learning works. Okay, so let me give you a very brief idea of how this mechanism actually works, which is not very different from what we're doing today. First, when we get an image, like a digital image like this, they're given in terms of pixels. You know what pixels are, right? We actually break this image into just little tiny pics, and each of these little dots is a pixel. It's they call it a pixel stands for picture elements, right? An element of pictures. But when you have a file with all these pixels, it doesn't tell you what the image is. Right? The first step you have to do is start from a data that is represented in pixels and get to another representation based on features. Because human brains don't recognize pixels, right? The sensors, the cameras do. So for the first thing for the machine to do is take a pixel, image based on the pixel, and start to extract features that are meaningful. Okay? And that is what we use, what's called a convolutional neural network. It's a type of machine learning algorithm you do. And what you do is you start from like a 1 million pixel image, which is very large pieces of data, and then we actually go through a compression, and actually extract the key features by ignoring a whole bunch of other things that really don't matter. Okay? Because at the end of the day, in a cat picture, there aren't 1 million pixels, million features that we pay attention to. There's only a few dozen of them. And then based on that, we can tell. So this process is convolutional neural networks that actually compresses the image to focus on features that matter. Okay? And we actually use that in a manner called supervised learning. And supervised learning is like a parent telling the baby, that's a dog and that's a cat. Okay, so it's what we call, it's a label data, meaning I have a bunch of cat pictures that are labeled cats, and a bunch of dog pictures that are labeled dogs. And what I do is I run through this algorithm and then tune the algorithm in such a way that all the dog pictures show up in one side and all the cat pictures on the other side based on these features. Okay, so that's called supervised learning. And then once you extract these features, then you go into classification. And the classification usually uses what's called a fully connected neural network. And basically ask the question, is it a dog or is it a cat? And then by the time you actually optimize these in the feature space, they get separated well enough, and now you have a model that can differentiate from a dog from a cat. Very similar to how people learn. So this is a very well-defined algorithm today in machine learning, right? We do classification all the time. We even have services on our cell phones that if you take a picture, it will recognize somebody and recommend for you. Because it actually has done all this feature extraction and says this person should be Megane. This person is Biz. And they would do all of that. So this is very common, very widely used today. But the question is, can you do this with a quantum state? Okay. So in collaboration with with a company, Hyundai Motor Company, we actually decided to look at this toy problem, where this is the image data set of 43 classes of road signs in Germany. Okay, and this data set is available on the web. Each of these is actually a relatively small image. It's a 32 by 32 pixel image. And what we do is first we have to actually do this convolutional network to extract features. And it turns out that the quantum computers we have today are not powerful enough to do this very complicated feature extraction. So for now, we actually utilize classical convolutional networks to actually compress the image and then extract these features. Okay? And then we use a quantum computer to see if we can actually classify them. Okay? So one of the problems is, then in the next picture I'll show you the result of the scale of the problem. One of them is our quantum computer is very small, meaning we can only handle a very small number of features, in this case 4 quantum bits worth of features. And then we expand it to 8, and then we extend it to 16. So we actually make the model more complex. And that will give us a better ability to differentiate different pictures. And then we also scale the size of the problem. First, we start with, can you classify A and B? Just 2 different pictures. So can you differentiate between 4? Can you label between 8 and 10? So we go in that scale. Okay? So this shows an example of running this classification algorithm on a quantum computer. And this one, we use 4 qubits, meaning it's a very, very small quantum model. So what we do is we first compress it down into a 4-element vector. And then we load this 4-element vector onto a quantum computer. And then we go through this model of classification. And when you're only trying to differentiate between 2 numbers, 2 different categories, 2 different types of images, and this is the accuracy, we can actually get it pretty good on a very small quantum computer to be maybe 90%. For now, let's look at the orange bars. But as you go from on a very simple model, as you go to 4 different images, 6 different images, 8 and 10 different images, because the model is so small that it has a hard time differentiating between many, many different categories of numbers. So the performance degrades. But when we expand the size of the model to be 8 qubits and then 16 qubits, then generally the performance gets better. So when you go to 16 qubits, 2 and 4 we can actually tell pretty well. Our accuracy is like 95%. Even at 10, we can do 60%, which is pretty good. So this actually shows you that you can do classification successfully. Now the difference between the orange and the gray, the orange is actually we use ideal quantum model. Ideal means like error-free quantum model. And for these small quantum computers, we can actually simulate them on a classical computer that is near perfect. But the gray is what we actually extracted from our real quantum computer that actually contains some finite amount of error, and therefore the accuracy goes down. But you can see that it can actually do reasonably well here. All right, so here we show an example of classification, but our classical computers are so powerful. These big data, big gigantic billion-dollar data centers that we build can do this like this, right? So why? Why do you worry about quantum computers?
So Professor, when quantum computers are advanced more, does that mean that the original computers will be replaced completely?
You know, that's a fantastic question. Remember, quantum computer is a superset of classical, meaning from theoretical point of view, classical physics is part of quantum physics, and therefore classical computers are part of quantum computers. And the fact is that the technology for classical computers have been progressing over the last 70 years. So we have very, very advanced computers today. So, and whereas quantum computers, although in principle it can do things that classical computers can't, there are many, many things that classical computers can also do.
I see.
And from that perspective, the classical computers are so much more powerful. So instead of us thinking that quantum computers will completely displace classical computers, we have a huge infrastructure of classical computers today, yet we have these problems that are impossible to solve, that are very difficult to solve. So I think the first way this is going to work is if we can actually find a classical, a quantum, I would call a coprocessor, where it can actually be, run algorithms that classical computers cannot run efficiently.
Right.
As part of this bigger solution to make the overall computer much more powerful. This is called a hybrid model of quantum computing. I think that's the way it's going to go. And for all of the telephones and video conferencing and word processing where classical computers are doing extremely well, it's not worth building quantum computers to replace it. So I think the classical computers will exist for a long time to come. I don't see it going away, but quantum computers can add to its capability by a lot. All right. So, so what does this quantum add to machine learning? So, we saw an example in the factoring algorithm or the code cracking, where quantum computers can do things that classical computers cannot do. So there, the use case is obvious. But things like machine learning, classically, we're doing really well. Like we have these language models that can actually write essays for you and do all of these things. So when you have all of this, why do you worry about quantum computing? Now, from all of these studies, although they're simple, we learned a few things. First, we learned that, remember, we're trying to build this model in some mathematical space that captures the structure of the data, right? These features and how these features actually separate A from B. These are all structures that we have in the data. It turns out that when you think about building a large language model that can actually write essays for you, like ChatGPT and all these, that requires a huge model. They typically have models with tunable parameters that are counted in the hundreds of billions of parameters. And you need huge amounts of data to actually train it so that it can actually start to do predictable things. So when you have that much data, you can build an AI model that's pretty accurate. And that's why it took us 50 years since the first AI idea, which was the awarded Nobel Prize last year for the Hopfield model in the 60s, to actually build it. We needed huge amounts of data. And the reason that we built it in language is, guess what? We spent the last 30 years digitizing every document we have. Not to build machine learning, but because we wanted libraries to go online and we want to be able to distribute information through the internet and so on. And then we started creating new content directly digitally, right? So now we have this massive amount, like billions and billions of documents of language that are generated and available in digital format. And that's the only reason we can actually train a machine learning model. But there are so many other examples where we don't have that kind of data. For example, if somebody wants to look at a mammogram and see if there's cancer, we don't have that much data. Right? So in this type of many, many examples, we don't have enough data to build reliable enough models. Now, it so turns out that what we're observing is you can make this very complicated structure in quantum space much more efficiently, meaning with much fewer parameters. What this means is there is a potential to build quantum machine learning models where you can train and start to predict reasonably accurate things with a lot less data. Remember we talked earlier about this hallucination where ChatGPT will create if the data is not sufficient, they would actually say things that doesn't make any
Yeah.
sense. If you can make more efficient models with less amount of data, you can actually capture the structure more efficiently. Then you can actually start to apply this machine learning and AI to application areas where we don't have that much data. And then I think that can open up new possibilities. Now, I'm not saying we know how to do it yet, but these are the possibilities that quantum computing can open up for you. Okay? All right. Now, this is a picture that we took a few years ago where, this is a manufacturing floor, or we call it quantum data center. And each of these big boxes are quantum computers. Okay? So, these quantum computers are, pretty big devices that, fill up a good chunk of a room today. Very similar to the IBM computers you saw in NASA's training center in the movie Hidden Figures. Right? These are big machines. We're kind of in that stage today. But if you go and dial back in time, just about 10 years ago, this technology, which we commercialized several years ago, looked like this. Right? It's a research lab, and it has all of these equipment all over the place, very complicated wiring, lots of things that has to be tweaked. And most importantly, we had lots of people who were sitting in the lab and tweaking this all the time to get this experiment to work. Okay? That was the scientific phase of this. What we have done over the last 10 years is to take that and turn it into a system that we can design and manufacture and operate more reliably. And over time, this bench scale system, which is, this one in 2018 picture is kind of the prototype for the quantum computers we have commercially available today. But in some of our research front, we're starting to make them much smaller and much more compact and much more reliable. Ideally, and then, more recent times, people are starting to use some of these chip scale technologies like this to actually start to make them much more compact. So I think there is a progression of technology into the future where a machine like this, yes, these are handcrafted machines. You can't make them and deploy them to individuals and so on. We don't have that technology yet today. But we can see a future where a lot of these manufacturing can actually come onto more advanced and integratable technologies to eventually get to a point where we can build quantum computers. And we can also build quantum supercomputers, quantum data centers, where many, many, many of these quantum computers can be connected together to build a much larger system. So that is actually a technological path. It's kind of like Moore's law in quantum physics. But we don't know how to remember, Moore's law didn't start until 1970. In the 1960s, we're building computers that kind of look like this, and we didn't know how to do Moore's law. So that technology of the future is yet to be invented. It's for all of us to actually make some effort, be creative, and dive in and create that technology.
So, Professor, with
Yes.
with all the lectures that we've heard so far, we had math, we had robotics, AI, and now quantum computing. Now it all feels like it's part of the same, one shared universe. Would you say that's true?
Absolutely. Well, first of all, there's only one universe, right? And we are trying to first understand it. We're trying to see if we can have a model of a universe we can create, just like the dog and the cat picture, some model in our brains that we can create to understand and predict how the nature will behave. Okay? Some of that is logic, which is what math does. Some of that is structured data, in real-world data, that is not random, but structured data. And that features that we extract is what help us start to build knowledge and models. That's what AI is doing. Robotics is, can we actually now control that into a real-world motion? And can we actually start to affect the real world? Just like we do when we build stuff or when we write on a piece of paper. And quantum is actually the real underlying principles that are different, that we only discovered 100 years ago. These are the way that nature works. So science is an act of trying to build a model in our brain so that we can actually understand the nature. Now, when that knowledge becomes very mature, and with the help of robotics, like when people move to, we can actually start to create technologies and use that knowledge to our advantage to build computers, to build the internet, to build the AI machines, to build quantum computers, to actually build more and more powerful tools by which human beings can be more productive. That has been an evolution. And I think in that sense, all of these are different aspects of understanding and affecting the universe around us. Now, of course, the most important question is we can do a lot of good or we can do a lot of bad. So that decision of how we are going to develop and utilize that technology to the human good is going to be the core question that each and every one of us have to have in mind as we make the progress in this direction. All right, so we had a great discussion about what quantum computing is, what quantum physics is, and how that is starting to kind of become practically interesting enough technology for us. I'd like to see if you have any other questions you wanted to ask in general, either about or outside the scope of the lecture we just
Professor, I do have a question. So when quantum computers become more common, so obviously rich countries can afford more than the poor ones. I want to know about your perspective, whether it would make the world more unfair?
You know, that's a fascinating question. Last summer, I participated in a meeting at UN in Geneva, and they were asking exactly this question, right? And in general, I think technologies have always created a larger discrepancy because technologies create more productivity, and people with access to that technology become more productive, while people without the access remain less productive. So that gap can actually continue to grow. And that is not only a problem of quantum computing. I think that is the nature, at least the way that technology has impacted our society. You know, I think that's a fascinating question. And it's going to have a lot of factors outside the technology area that's going to drive this. So a lot of this question is, you know, how do we actually make sure that these more advanced technologies become more democratized, meaning more easily accessible to a broader public? And I think there are some good news about this. The good news in my mind is the infrastructure we have today that we did not have 50 years ago. It's called the internet. Now, a lot of population around the world have access to internet today. It became relatively ubiquitous. Now, of course, in the beginning, people who had internet versus people who didn't, actually there was a discrepancy in that too, but the cost of the technology have become low enough that everybody has internet. What that allows you to do is if we can create a very expensive quantum computer somewhere, but if we can actually continue to reduce the cost of it, you can allow people from anywhere in the world, even if the quantum computer is not in front of you in your room, you will be able to access that. Okay, and so I think over time it's a question of you know, how we make the cost and the number of devices available to be deployed. And today you can see cell phones everywhere, right? Now, on the flip side is the question and the challenge. That this discrepancy is always, I think there is a huge factor of human innovation that goes into taking advantage of these new tools to become more productive. And that's why, for example, if you think about Korea in 1950s, we're very poor, very low technology levels. But when people dive in and add more energy and innovation into it, you can catch up. Which means that this advanced productivity, once you get accessible to it, it's really up to the people to innovatively utilize that to try to get ahead. So I think of course, making it available to larger population will be an important technological advance. But I also challenge people to be creative. Once you have these tools, it's really up to your innovation and imagination to try to get ahead using these tools. And that can come from anywhere because this is going to increase your productivity by a lot.
If it's correct, but the conditions to to maintain a quantum computer are quite difficult, right? It has to be like very cold.
Yes, that's a great question, and it is true today with this early stage technology we have. It's very delicate. It's very difficult to deploy at large scales because you need experts to run it. But again, I think with the technology becoming more mature, I think there will come a time. I mean, today, computers are just like that in the 60s. It requires some experts to maintain it. But today, we can throw it in our pocket. We can even dive into the ocean, and the computer will still function. And that's a maturity of the technology. So I think as the technology gets mature, the cost of not just purchasing, but installing, operating, and maintaining a quantum computer will actually go down to a point where if it breaks, we can throw it away. And well, throwing it away will have an environmental impact. But I think there will come a time where the cost of all of these things will go down. And as cost comes down, it will become more accessible to larger and broader public.
I mean, this might be a dumb question, but as you showed with Moore's law, it kind of slowed down considerably from the past. So do you think, have we reached a limit in computing with quantum computing, or is there even something beyond quantum computing, like in the years to come?
Yeah, that's a fascinating question, right? So we are actually, for quantum computing, I think we're kind of pre-Moore's law, right? So we're still in the very, very early stages. And that Moore's law lasted, I mean, it's been going on for like 55 years, even a long time. And even some part of it kind of slows down. The actual computational value that we extract out of it continues to improve. Meaning, I don't think we'll come to a point where a computer today or at any given time is the same as a computer from 10 years ago. It will always continue to get better in some measure. Right? So I think that in that sense, although the number of devices may saturate, I think the actual capability that we utilize will continue to improve. Having said that, for quantum computers, we're still in the very, very early stages. Exactly what that law is going to look like and how long it's going to last, how many decades it's going to last, we just don't know that. So I think it's a little bit too early to say what is the end point of quantum computing slowing down and what the next thing is. It's really for you guys to think about, but I don't think that time will come within my lifetime. So I'm going to focus on what we can do with quantum computing. All right, so we live in a very exciting time where some of the very fundamental understanding of new science to technologies that can actually drive different change in our lifetime. Now, it used to take a long time, right? It used to take a long time, but that cycle is getting shorter and shorter and shorter. So I think we live in a very interesting times where learning new things and understanding new science can actually affect kind of new technologies and that will affect our lifetimes in a relatively short times. What that means is we need people to actually cross all of these boundaries. The good news is we'll have tools like AI and others for individuals to be so much more productive and start to span across many different regions. So I think one of the take-home messages I would love to share with you based on my experience of starting out as a scientist to becoming an entrepreneur and eventually kind of coming back to how we actually think about education on our next generation is the world is changing. The world changes. And sometimes that's scary because when the world changes, the way that we have become used to may or may not persist. And sometimes we think about how do we adapt to the world that is changing. But an even more important question is the world doesn't change on its own. The world changes because of the things that people do. And the way the future is going to get shaped, it's really up to you and all of us to make of it. So we can actually worry about adapting to a fast-changing world that is unpredictable, or we can actually go and drive that change to the way that we think is valuable. Quantum computing is an example where science has led to very exciting early part of the industry today, but it is driven by some people who had passion and who was dedicated to making that change happen. And it is being shaped into the form that these people actually envision. So what I'd like to conclude is the future is not there predetermined for you. And that's the recognition of the 21st century science. Okay? What that also means, it's really up to us to create that future, whatever it is. And let's do it right. Because as the impact gets broader more quickly, if we do a lot of damage, it may be very difficult to undo. With that note, I'd like to thank you for your attention and wonderful discussions with you.
Thank you so much.
Thank you.
네.